In the heart of Europe, buried beneath the scenic landscapes of France and Switzerland, lies a marvel of modern science, the Large Hadron Collider, LHC, at CERN. This colossal machine, spanning a whopping 27 kilometers in length, is not just a massive tunnel. It's a portal to the secrets of the universe. At its core, the LHC is like a giant racetrack for tiny particles called protons. Picture it like this. Imagine the LHC as a colossal tunnel, with two lanes running in opposite directions. Inside these lanes, scientists send protons, particles smaller than atoms, whizzing around at speeds close to the blink of an eye. These protons are so small that if you could shrink yourself down to their size, you'd be smaller than a grain of sand in a vast desert. But here's where the magic truly happens. It's not just a matter of firing a few protons at each other. No, scientists at CERN unleash an astonishing 100 billion protons in each direction, creating a collision course of epic proportions. And you won't believe how many of these tiny particles actually collide. On average, out of the staggering 100 billion protons hurtling towards each other, only about 50 or 60 of them manage to collide. To put this into perspective, imagine standing in the midst of a bustling city with billions of people rushing past you. Now imagine trying to spot just 50 or 60 individuals out of that massive crowd. It's an incredibly tiny fraction, yet each collision holds the potential to unlock profound secrets about the universe. This remarkable feat is repeated over and over again, with scientists observing these collisions a mind-boggling 30 million times per second. With approximately 3,000 bunches of protons hurtling through the LHC, each containing over 100 billion particles, the result is an astounding 1 billion collisions per second inside this massive machine. But why go through all this trouble? What's the point of smashing particles together at such incredible speeds? Well, the answers lie in our quest to understand the building blocks of everything around us. The theory of the Big Bang tells of a time nearly 14 billion years ago, when the universe was a much hotter place. But how can we know what the universe was truly like so long ago? Well, a time machine would work, but that technology hasn't been invented. So scientists do the next best thing. They use particle accelerators to recreate the conditions of the early universe in the laboratory. In this way, data generated in particle physics experiments can offer a glimpse into the earliest moments of the cosmos. However, it's important to understand both the power and the limitations of this approach. Big Bang theory imagines a series of epochs, each with a characteristic energy and temperature. Not all of these epochs are well understood. For instance, the earliest moments of the universe remain elusive. They are shrouded in mystery, and our understanding is merely a series of educated guesses. However, in a fraction of a second, the conditions of the early universe quickly transitioned to ones that are testable by modern technology. The LHC, as we know, is the world's most powerful particle accelerator in operation, accelerates pairs of protons to nearly the speed of light and slams them head-on into one another. The proton's motion energy is converted into heat energy that reaches temperatures 100,000 times hotter than the center of the sun, temperatures that were last common in the universe less than 1/1,000,000,000th of a second after the universe began. Other experiments have studied the behavior of matter when the expansion of the universe cooled enough such that the laws of particle physics no longer applied, and the era of nuclear physics commenced. By the time the universe was just a few minutes old, the makeup of the universe and the laws that govern it were already locked in place. 3 minutes after the universe began, the nuclei of the primordial hydrogen and helium that made up the first stars already existed, though it would take hundreds of thousands of years before the universe cooled enough to make atomic hydrogen and helium. After the formation of atoms, gravitational forces dominated for hundreds of millions of years, leading to the creation of the first stars. a point at which nuclear physics once again played a crucial role. So, which epochs of the early universe do particle accelerators study? Let's begin the story during an epoch for which the story is not yet fully understood. At the very early time of about 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the universe began, cosmologists believe that the universe experienced a period of expansion at speeds that exceeded the speed of light. This is called the inflation epoch. There is a lot of circumstantial evidence that this occurred, but there is no definitive confirmation that inflation actually occurred. As of this writing, inflation remains a theoretical proposition. At the end of inflation, the universe was hot and dense and quite different from the universe of today. The universe was far too hot for atoms to exist. The same was true for protons, neutrons, and quarks, which are the particles found inside protons and neutrons. Even mass and electric charge are thought to have not existed. So, the entire universe was full of highly energetic and massless particles. Scientists are not entirely sure what happened in the universe before about 10 to the power of minus 13 seconds. One reason is that we lack the technology to concentrate enough energy to study those early times. However, the LHC allows them to collide together pairs of protons traveling at nearly the speed of light. The maximum energy generated in one of those collisions will generate temperatures last common in the universe 10 to the power of minus 13 seconds after it began. With that capability, our understanding of the evolution of the universe improves dramatically. At about 10 to the power of minus 12 seconds, an energy field called the Higgs field came into existence. This field interacted with the matter in the universe and gave particles their mass. At the same time, electric charge came into being. Instead of a universe in which only massless energy existed, particles with mass came into being. These particles were called quarks and leptons. Today, quarks are found only inside protons and neutrons, and the most familiar lepton is called the electron. The Higgs boson, which is a vibration of the Higgs field, was discovered in 2012. However, in that early time, quarks were not restricted to exist in protons and neutrons. Quarks could roam freely. After all, the universe was too hot for protons and neutrons to exist. If you placed a proton in that early universe, it would effectively melt and let its constituent quarks run freely. Much like if you put an ice cube on a hot sidewalk, where the heat melts the ice and water can move around. Time progressed, and the universe expanded and further cooled. By about 1/1,000,000th of a second, or 10 to the power of minus 6 seconds, the universe cooled enough that quarks could no longer wander freely. Strong forces gathered the quarks together, forming protons and neutrons. Electrons existed, as did an unfamiliar particle called a neutrino. Neutrinos are very low-mass subatomic particles that interact very weakly with matter. In the modern day, they are generated in nuclear reactions, and they don't have much effect on the universe. However, the density of the universe at 10 to 6 seconds was so high that neutrinos interacted fairly strongly with the protons, neutrons, and electrons that dominated the universe. By the time the universe was about 1 second old, the density of the universe dropped enough that neutrinos no longer interacted with other forms of matter. Indeed, our current universe is full of neutrinos that last interacted with matter a scant second after the universe began. Very sensitive experiments are underway which should be able to detect these primordial cosmic neutrinos within the next decade. Over the next several minutes, the expansion of the universe continued to cool to low enough temperatures that protons and neutrons could begin to clump together to form atomic nuclei. Had the density of the universe stayed high, the nuclei of all of the known elements could have formed. However, the rapid drop in the density of the universe only allowed for the simplest nuclei to form. By about 3 minutes after the universe began, hydrogen nuclei, single protons, and helium nuclei, 2 protons and 2 neutrons, had formed, along with rare isotopes of hydrogen, deuterium, and tritium. By 3 minutes, the universe consisted of about 75% hydrogen and 25% helium. That's by mass ratio. If you simply counted hydrogen and helium nuclei, the ratio was about 92% hydrogen and 8% helium. The difference is because helium nuclei weigh 4 times as much as hydrogen. There were also trace amounts of other substances, but for the most part, all other elements would not come into existence until they were formed in the center of stars. So, this is the story of how particle accelerators teach us about the early universe. At much later times, about 380,000 years after the universe began, the universe cooled enough for those hydrogen and helium nuclei to capture electrons, and the first atoms came into existence. And the story was certainly not complete, as gravity eventually gathered those atoms into hot clumps that eventually became stars and galaxies. Our understanding of the nature of the universe from the very beginning to just a couple minutes after it began is quite sophisticated and guided by firm measurements. More importantly, our understanding is not from theoretical speculation, but rather from complex and detailed measurements. Using giant atom smashers, scientists can literally recreate the conditions of the early universe and see how things work. The drive to understand how our universe began is an ancient one, with the first stories found in some of humanity's earliest writings. Through a combination of astronomical observation and experiments performed inside enormous particle accelerators, scientists are beginning to have a very clear understanding of how it all began. One of the most anticipated outcomes is the observation of new particles beyond those predicted by the Standard Model of particle physics. The Standard Model successfully describes the known elementary particles and their interactions, but leaves many questions unanswered, such as the nature of dark matter, the existence of additional dimensions, and the unification of fundamental forces. Discovering new particles could provide crucial insights into these unresolved mysteries. One class of particles that researchers hope to find are those associated with supersymmetry, or SUSY, a theoretical framework that proposes a symmetry between fermions and bosons. SUSY predicts the existence of supersymmetric partners for each known particle, which could address some of the shortcomings of the Standard Model and provide a potential explanation for dark matter. Additionally, the LHC experiments could yield indirect evidence for dark matter particles. Although dark matter itself cannot be directly detected by the LHC, its presence could manifest through the observation of missing energy or other anomalies in collision events. Detecting dark matter particles would represent a significant breakthrough in our understanding of the universe's composition and structure. A new idea to link dark and visible matter is to search for particles called axion-like particles, or ALPs for short. The axion was first introduced to explain one of the most well-known questions in particle physics, called the strong CP problem, the puzzle that matter and antimatter behave the same for the strong nuclear force, but not in the weak nuclear force. Since then, axions have evolved to the more general class of ALPs, which have become widely included in theories of new physics. For instance, ALPs could act as mediators in the interactions between known and dark particles. The Quantum Universe Cluster of Excellence has a well-established program focusing on ALPs from both the theoretical and experimental perspective, but searching ALPs at the LHC is relatively unexplored. One of the properties of ALPs is that they interact more with heavier particles, making it interesting to explore how ALPs interact with the heaviest known particle, the top quark. This preferred interaction of ALPs suppresses their decay to other, lighter particles. By restricting ALPs to interact solely with top quarks, we further constrain their possible decay channels, and, as a result, allow them to have long lifetimes and to travel macroscopic distances before converting into other particles. Such long-lived particles could be created at the LHC, and the products of their decays could be registered by detectors such as ATLAS or CMS. Explicitly searching for particles decaying away from the collision point allows you to reject many typical and uninteresting processes. Due to quantum mechanical effects, long-lived particles with a given average lifetime can exhibit different decay lengths within the detector or even outside the detector limits. Some theories suggest that there may be extra spatial dimensions beyond the 3 dimensions of space that we experience. The LHC could provide evidence for the existence of these extra dimensions by detecting phenomena such as microscopic black holes or deviations from the expected behavior of known particles. Moreover, the LHC experiments could reveal evidence of new forces or interactions between particles beyond those described by the Standard Model. These new forces could have profound implications for our understanding of the universe's fundamental properties and could potentially lead to the development of new theoretical frameworks. In addition to searching for new particles and forces, the LHC aims to further study the properties of the Higgs boson, which was discovered at CERN in 2012. The Higgs boson plays a crucial role in the mechanism that gives mass to elementary particles and is a cornerstone of the Standard Model. By studying the properties of the Higgs boson in detail, researchers hope to gain a deeper understanding of the mechanism responsible for mass generation and potentially uncover hints of physics beyond the Standard Model. Furthermore, the LHC experiments can provide valuable data for precision measurements of known particles and interactions. By precisely measuring the properties of known particles, researchers can test the predictions of theoretical models and search for discrepancies that could indicate the presence of new physics. Overall, the LHC holds the promise of transformative discoveries that could reshape our understanding of the universe. Sadly, it's now been a full decade since the Higgs boson was discovered, and it was determined to have only the properties predicted by the Standard Model. Thus far, there's no new accelerator evidence, directly or indirectly, for any fundamental particles that aren't accounted for by the Standard Model, and for any interactions or decays that aren't predicted by the Standard Model. Given that this is the case, you can find many pessimistic takes on the field of particle physics as a whole, and find many, physicists and non-physicists alike, who view large colliders as an expensive folly whose time ought to come to an end. These takes are all not only disingenuous, presenting a heavily slanted and overall inaccurate version of the actual truth, but they miss the fundamental point of not just particle physics, but physics in general, as a scientific discipline. Physics is an experimental science, and the way you advance an experimental science is to subject the universe to inquiries that you've never subjected it to before, and listen very closely and carefully to what it tells you. That's how you learn more about the fundamental nature of reality. This is true in every physical field. If you want to study the low-temperature universe, you always strive for that next significant digit in your quest for absolute zero. From a few Kelvin to millikelvin to microkelvin to nanokelvin, and now down into the picokelvin range, each step colder reveals more properties of matter under extreme conditions than ever before. If you want to study the astrophysical universe, you push the frontiers of what you can see in terms of depth, by building larger observatories, in terms of wavelength, by probing every range from gamma rays down to radio waves, in terms of clarity, by going to space, and in terms of what you measure, by measuring not just light, but also cosmic particles and gravitational waves. And if you want to study the world of particles, you always strive to measure their properties and behavior in new realms and with greater precision as compared to everything prior. In other words, the two frontiers we need to be pushing, if we want to understand the universe of particles better than we understand them today, are to probe the universe at higher energies and/or at greater precisions, with more collisions than ever before. It's possible to go to higher energies, but the only ways to achieve them are to either increase the physical size of the accelerator, which realistically requires building a new accelerator, or to increase the strength of your bending magnets. It's historically been considered worth it to build a new accelerator when you can increase your energy by a factor of 7 to 10 or more, which is the energy leap that was made from Fermilab's Tevatron to CERN's LHC, and which is the planned leap from the current LHC to the proposed Future Circular Collider, or FCC, the leading prospect for humanity's next particle collider. The €20 billion machine would have a 91-kilometer circumference and aim to smash subatomic particles together at a maximum energy of 100 tera-electron volts. For comparison, the Large Hadron Collider achieves maximum energies of 14 tera-electron volts. The new device would smash particles against a hard surface instead of against each other, which is the technique currently used by scientists to figure out what the universe is made of. The collider is part of CERN's Search for Hidden Particles project, or SHIP for short. This is a project 10 years in the making that will study some of the weaker particles in space. Dr. Richard Jacobson, senior staff physicist at CERN, said this project could be a huge breakthrough that redefines how scientists think about the creation of the universe. As Jacobson said in an interview, SHIP is one of those potentially paradigm-shifting experiments that could really drive us into a whole new regime of knowledge, not just about our universe, but about our position in the universe. Much of what we have assumed up until now could actually be quite different. All of what we are able to see with our naked eye from space, including stars and the planets, composes about 5% of the actual matter in the universe. The other 95% are so far split between roughly 27% dark matter and 68% dark energy. Scientists use the Standard Model, which recognizes 17 different particles, to explain what the universe is made of. In 2012, CERN scientists discovered a new Standard Model particle called the Higgs boson, with a Large Hadron Collider, a discovery that won them the Nobel Prize in Physics a year later. Since then, scientists have been unsuccessful at using that same collider to measure the hidden particles that also possibly make up dark matter and dark energy, but that are not part of the Standard Model. Hidden or ghost particles are invisible and have weaker connections than the particles scientists have already discovered, making them difficult to detect. It's possible that these particles make up some or the rest of the universe. New particles in the Large Hadron Collider already at CERN can be detected up to a meter from the site of the collision, but hidden particles remain invisible for much longer before revealing themselves. So, the detectors in the new collider for the SHIP project will be placed further away and will produce more collisions against a fixed backdrop as a way to finally identify these particles. The SHIP project will be working alongside the other CERN experiments, including the Large Hadron Collider. Construction on the SHIP's new underground facilities will start in 2026, with the first experiments taking place around 2032. The Future Circular Collider, on the other hand, will start sometime in the mid-2040s, but will not be at its full potential until 2070. All of this is really worth waiting, but also to recognize that it will take more than a decade to construct it. But in the meantime, LHC just completed a major part of an enormous upgrade to what's being called the HL-LHC, or High Luminosity LHC. In astrophysics, luminosity refers to how bright an astrophysical source is. In particle physics, it's how luminous, or rich in particles, the beam is. By creating more bunches of particles that collide more frequently, and by increasing the number of particles that collide when two bunches cross each other, the current incarnation of the LHC has already broken the all-time luminosity record for particle colliders. In fact, over the next 10 to 15 years, the LHC will take somewhere between 40 and 50 times as much data as it's cumulatively taken so far, since its first turn on in 2008. In other words, the LHC data we've collected and analyzed so far represents only about 2% of the total data that the LHC will wind up accumulating. The LHC measures the total amount of collected data in what we call inverse femtobarns, and had collected 150 inverse femtobarns by the close of operations in 2018. The HLLHC will collect over 250 inverse femtobarns each year when it's complete. With that data, the LHC will be able to test the standard model in an unprecedented series of ways. They'll be able to create greater numbers of Higgs bosons than ever before, testing whether it decays according to the standard model's predictions to better than Mabur 1 part in 100 precision. They'll be able to test lepton flavor universality, currently one of the 3 still-standing standard model anomalies, along with the W boson's mass and the muon's anomalous magnetic moment, to unprecedented precision. If it's a real problem with the standard model, this will undoubtedly push it over the gold standard 5 sigma threshold. They'll be able to test whether the CDF collaboration's measurement for the W boson's mass matches their value, with much more, albeit less clean data, than Fermilab was ever able to collect. They'll be able to test top quark and bottom quark physics to better precision than ever, either confirming the standard model's predictions or running counter to it. And perhaps most excitingly, they'll look for clues of new physics in places where we might not expect it. In the meantime, let's cast your mind forward 150 years and picture a truly wild piece of infrastructure, a particle collider that circles the entire moon like a belt. It might sound outlandish, but the physicists who proposed this idea in 2021 say that the vast structure could be possible in the next century. Particle colliders propel charged particles like protons and electrons together at high speeds. On Earth, some are circular, like the LHC in Geneva, Switzerland. Others are built in straight lines. Both designs help particles reach phenomenal speeds. The energy from the collisions can create matter in the form of new particles, including some of the largest ones that we know of, like the Higgs boson, a fundamental particle that helps give other particles mass. So having the extra space to build a bigger, more powerful particle collider could potentially lead scientists to the discovery of other new particles. These particles help to glue together disparate physics ideas and move us toward a more complete understanding of the universe. A megastructure on the moon, for its part, could enable particle acceleration that reaches 14 quadrillion electron volts, or about 1,000 times more energy than the LH, the most powerful particle collider on Earth. According to James Beecham, PhD, a particle physicist working for Duke University who helped theorize the lunar collider, we have big open questions in science and particle physics, and we don't have any more theoretical hints as to where we should go to solve them. Building this kind of massive infrastructure on the moon may seem like an insurmountable challenge. But, Beecham says, the steps to do so are both practical and possible. Step number 1. Send the workforce to the moon for surveys. First, scientists will need to see what materials are available on the moon and what they'll need to bring from Earth. The collider could use regular supercooled magnets or higher temperature, approximately 100 degrees Kelvin or 173 degrees Celsius. Magnets, so researchers need to determine whether or not there are enough naturally occurring materials on the moon to make the higher temperature magnets. If there are, that could save a lot on transportation costs and infrastructure because cooling to near 0 degree Kelvin requires so much energy. Transporting tools and building materials through space is also incredibly expensive. Tunnel boring machines alone can weigh over 1,200 tons, about 240,000 pounds. And NASA estimates that each pound of payload costs $700 to send into Earth's orbit, let alone the moon's orbit. For context, the Apollo program cost an inflation-adjusted $280 billion. Step number 2. Consider how the collider will wrap around the moon. You can take the circumference of a spheroid at any point or location, so the collider doesn't have to wrap around the widest part of the moon. Scientists say there are great circle routes around the moon that avoid changing elevation, for example. Step number 3. Set up manufacturing infrastructure. Initially, mining for materials will be the highest priority. The best option for a moon-based collider would be to use iron-based, high-temperature superconductors, because it looks like the moon is full of accessible iron, Beecham says. Step number 4, bore out tunnels for the collider. Beecham says the moon's surface temperature variations are an immediate problem. An array of superconducting magnets will partly power the particle collider, so the entire structure must be temperature controlled. The day-night temp variations on the moon are so large that at least for half of the time, it would be too hot for the magnets to even operate, Beecham says. Beecham notes the best bet is to bury the tunnel at least 100 meters underground, where it will still require some cooling, but not nearly as much. At that depth, the collider is also exempt from the moon's day-night cycle. That helps to maintain its temperature equilibrium. Step number 5, determine a power source. The collider will require so much energy that even all of the existing nuclear fission power on Earth, which supplies about 10% of our total energy production, wouldn't suffice. It's estimated that the Moon Collider will use tens of terawatts of energy, which is closer to what all of humanity uses each day. That number is about 15 terawatts. Here, the scientists suggest using a solar-powered Dyson sphere, an imagined space superstructure that can directly capture energy from a nearby star, see below. Step number 6, build the collider and the infrastructure to work from home on the moon. Most people who study the Large Hadron Collider aren't on site because they receive huge quantities of data that they can study from anywhere. Beecham believes that the Moon Collider would be no different. But we do need to figure out the best way to beam large amounts of data from the moon to Earth. More importantly, besides a skeleton crew for maintenance, people on Earth will need to be able to operate the collider. That means something like your remote virtual desktop for your job, except your job is on the moon. Naturally, there are plenty of roadblocks that could crop up while planning a mega infrastructure project so far into the future. But for now, Beecham is pleased that the collider could at least bring together some of the greatest minds in science. Let's harness the power of these people who are really set on going back to the moon. Let's get them to focus on lunar collider projects that are for the good of humanity. Everybody could win with such a project. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.